Alright everyone, I decided to make a video as I was generating your final exam review key, so that you'd also not only know the answer but also how to figure out how to go about figuring out these problems. And so just going to run through as many of these as all the way to the end. And so here we go. So the first thing is reviewing conversions. And so when we do conversions, remember that we need Mega King Henry died, and actually that one's capitalized, died unexpectedly drinking chocolate milk, micro nano pico, 10 to the 6, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 6, negative 9, and negative 12. And so if that helps you, you can just jot that down. That is not on your blue periodic table. So that you got to memorize that. So here we go. 350 grams. Grams is U. And so I'm going to set up my conversion factor. Grams on the bottom, and I want kilograms on top. Kilograms is bigger, and so I'm going to put a 1 there. And then I'm going to figure out how many spaces, how many powers of 10 between kilo and grams. So kilos here, grams is U, base unit, and so that would be 3. It's going to be 10 to the 3rd. So in my calculator, I'm going to do 350 times 1 divided by E3. And I have to do, my calculator, I have to do 1E3. Okay, and I get 0.35. Okay, so 0.35 kilograms. Grams cancel, and I'm left with 0.35 kilograms. Okay, next one. Let me do it over here. 0.90 centimeters. And I want to get into meters. So meters are a base unit. And I have centimeters. Meter is bigger. Remember, how I determine that is whatever is closest to mega. Mega is the biggest unit. Pico is the smallest that we have on this line. So between U and C, there's 2 tens. So 10 to the 2nd. And if you do it this method where you put a 1 by the bigger unit, the exponent will always be positive. So that's why I like to do it this way. So 0.09 times 1 divided by 1 E2. Okay, and I get 0.009. 0.0009 meters. Okay, next one, 2.13 kilometers. I want it into millimeters. So again, kilo is bigger, power of 10. Kilo is here. Kilo is here. Millimeters is here. So notice that it's the difference between them. So 3 minus 3 is actually 6. Okay, it's not 0, it's going to be 6. So it's kind of like this, moving along the number of line. So it's going to be 10 to the 6th power. And so I'm going to do that. 2.13 times 1e6 over 1. Okay, and that's this big number. I'm going to put that into scientific notation. Let's see. I want it in scientific notation. Where is my... okay, maybe I won't put into scientific notation. Oh, here we go. Okay, I want scientific notation. So there we go. 2.13 times 10 to the 6th power. Okay, moving on. Pounds to kilograms. So notice on the tests, you don't have to memorize that conversion. I would be giving it to you if we did have it on the test on the final exam. So 582 pounds. Pounds is on the bottom, kilograms, and notice I have to convert it into, oh, actually it is kilograms. So it's 1 kilogram per 2.2 pounds. And so 582 divided by 2.2. Okay, I get 260, I'm going to round that, 265 kilograms. Okay. Next, 800 to centimeters to feet. Okay, I'm going to have to use this conversion up here. And so I can't go directly to feet, I have to go inches first. So there's, in every 1 inch, there's 2.54 centimeters. Okay, and what I can do to save some space is I'm going to set up my second conversion. For every 1 foot, there's 12 inches. All right, so 812 divided by 2.54 divided by 12. Okay, that gives me 26.6 feet. All right. Next, 473.1 inches into meters. So again, I can't go directly into meters. I gotta go into centimeters. So 2.54, 1 inch. And then I need to get it into meters. So I'm gonna have to use my Mega King Henry. Meter is bigger, and then between meter, which is a base unit, and mil is a million, or centi. Okay, it's 2. 10 to the 2. So 473.1 times 2.54 divided by 1e2. Okay, which should be 12.0. All right, so those are conversions. Next one, 500 milliliter bottle of Coke, mass of 593 grams. Density, remember DMV is our density equation. And so we're looking for D, density. We have 593 grams over 500 milliliters, which is the volume. That's going to give me my density, or how thickly concentrated it is. So that would be 1.19 grams per milliliter. Okay. Basketball has a density of 0.856 grams per centimeter cubed. Remember that centimeters cubed is the same thing as 1 milliliter. So I'm just going to change that already. Okay, so we put that in for D. Volume is 3 liters. And what is the mass? We're looking for G. Now remember, we can't use this because the units are different. Liters and milliliters are different. And so I'm going to have to convert that into milliliters. So 3 liters. Okay, so liter is a base unit and it is bigger. It's U. And then milli, okay, is 10 to the 3rd. Okay. So that would be equal to 3,000 milliliters. Okay, so I'm going to cross multiply. So I'm going to do 3,000 times 0.8. We assume that's all over 1. And so grams is going to be the gram amount, our mass is going to be 0.856 multiplied by 3,000. And that's going to be equal to 2.57 grams. Oh, 2.57 times 10 to the 3rd grams. Okay. .57. Yep. Okay. That's our mass. Okay, next problem. What is a volume? It's another density problem. So 0.804 grams per mil is equal to 1.29 grams over volume. Okay, again, I'm going to cross multiply to figure out the volume since volume is in the denominator. So it's going to be 1.29 grams is equal to, because that's 1.29 times 1, 0.8 times V, 0.804 grams per milliliter times V. Okay, I'm going to divide 0.804 to get V. V is going to be equal to 1.29 divided by 0.804, 1.6. And notice grams cancel, I'm left with milliliters. Okay, a horse has a mass of 653 kilograms. Okay, then notice right away I want it in grams per milliliter. So I'm going to have to convert that 653 kilograms into grams. Oops. So 1 kilogram per 1,000, or 10 to the third. Okay, right, because kilo is over here. Gram is a base unit, so U, so 3 powers of 10 there. And that's going to be equal to, let's see, 653 times 1e10, 3, 6.53 times 10 to the 5, and that's in grams. The next one is 648. Let's see, actually 748 liters. Gotta get it into milliliters. So again, let's see. I'm looking at milli. So milli and base unit. Liter is a base unit. So 0 to -3, that's 10 to the power of 3. So that would be okay, 7.45 times 10 to the 5th milliliters. All right, and the last step, to get density, I divide the mass over the volume, and the density is going to be equal to, let's see, 6.53 E5 divided by 7.45 E5. Okay, and that's going to be equal to 0.88 grams per milliliter is the density of my horse. All right, so that's the conversions and density. We're moving on to the periodic table. We're going to label a whole bunch of stuff. This was unit 7. That first part that we just did was unit 1. So let me label it. This is unit 7. All of this was unit 1. Okay, unit 7 periodic table. So we're going to name the groups or families. So over here I have the alkali metals. And this is actually labeled for you on your periodic table. The next is the alkali earth metals, also known as alkaline earth metals. And they're called that because they turn things more basic when you put them in a solution. Okay, this block right here that I'm going to highlight in yellow. Okay, all of these guys. Okay, they're known as the transition metals. Okay, over here we have the halogens and the noble gases, also known as the inert gases. Okay, and then metalloids. So we have this kind of staircase over here. I'll label it in green. Okay, so we have aluminum, or actually, sorry, that's not aluminum, that's boron. Boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. Okay, so anything touching this staircase on your periodic table, they sometimes are metals, sometimes they're not metals. Or sometimes they behave like metals, sometimes they act like non-metals, and so they're known as metalloids. Okay, and that does not include aluminum. Actually, aluminum is a metal. Okay, so all those guys are metalloids. Okay, next, metals. So metals are all here, and I'll label it in blue. Okay, all these guys, including the transition metals, they're all metals. Okay, and we already labeled the metalloids. All these in the top right-hand corner, I'll label them in pink. Okay, these guys are nonmetals. Okay, valence electrons. So valence electrons, we start off with the furthest left. So the alkali metals have 1 valence electron. Alkaline earth metals have 2. Remember that transition metals can vary depending upon what it's connected to. Boron has 3 valence electrons. Carbon's family has 4. Then 5, 6, 7. Noble gases have 8. Okay, so those are my valence electrons. It's just basically which column it is. And valence electrons are, again, the outermost electrons. So, for example, let's say we have hydrogen, right? Hydrogen has 1 valence electrons. When we write a Lewis dot structure, it'll just have 1 dot that would represent the valence electron. And valence electrons are the electrons on the outermost orbital. So, for example, if I had lithium, lithium does have 2 electrons in its first orbit, but on its most outer orbit, it only has 1 valence electron. Okay, just like hydrogen. So everything in the same column has the same amount of valence electrons. Okay, so these guys would be the S block, and then these guys over here are the P block, P and S. And transition metals are D block, and of course the lanthanide, actinide series are the F block, but you don't have to know that. Okay, distillation. Distillation, remember, if I had a beaker with water in it, and I had a hot plate, and it's, if I heat it up, that water will become water vapor. And if I cool that water vapor, like if I capture it and kind of put it in a tube that leads to somewhere else, and I cool it into the second jar. Okay, if I cool it, okay, this would be a type of physical change, because although I'm heating the water, turning it into a gas, and then cooling it, turning it back into liquid, it's still water. It's water vapor. I can get it back into its original form. And so anytime you have something you can get it back into its original form, it would be a physical change. And distillation is a process we separate things because based upon its boiling point. Okay, BP, boiling point. Water boils at a certain temperature. So if I had something else in the water, for example, if I had salt in the water would boil away first, and it would leave behind salt, because salt boils at a much higher temperature than the water. And so if I had 2 liquids, so for example, if I had water and say, let's say I had water and some isopropyl alcohol in there, isopropyl alcohol boils at a lower temperature than water, so it would boil first. And so I could separate 2 liquids based upon their boiling points. That's all distillation. Okay, the formula for percent error, we use it when we're trying to figure out, for example, how off we are in a lab. Okay, it's going to be actual, the actual value that we're supposed to get. Actual is the value that we got in the lab. Theoretical would be the amount that it's supposed to be, and it'd be divided by theoretical. Okay, and that would give me my percent error. So, for example, if my actual value was very close to the percent. If I got pretty close to what it was supposed to be, it would be close to 0, right? So like if, for example, if my it's kind of like your test, right? If I got 90% and you're supposed to get 100%, and again, sorry, take the absolute value so there's no negatives. Okay, so that would be 10 over 10, or sorry, 10 over 100. So what is 10 over 100? Well, that's 10%. 10% error. Okay, 10% you got wrong. Okay, so that's actually pretty good. You want 0% error, or 1% error would be even better, but that's how you get percent error. Okay, appropriate metric units for volume. Okay, so we use either milliliters or liters. Mass would be grams. Temperature, we use degrees Celsius or sometimes Kelvin. We don't use Fahrenheit. More on that when we get to gases. Okay, we're going to classify the following as compounds or elements. Remember, elements are things we can find on the periodic table. Compounds are two or more elements combined. So let's see, NaCl would be a compound. Water is H2O, so compound. Nitrogen is an element. If it was nitrogen gas, it would be N2, but this is purely just nitrogen. Nitrogen gas would be a compound. Oxygen is also an element. Diamonds are made out of just carbon, so that's an element. Sugar is a compound. It's C12H, I think 22O12, something like that. So there's multiple, so it's a compound. Aluminum is an element. Pre-1982 pennies were made out of pure copper, and so that's an element. And then hydrogen is also an element. Okay, so if it says, for example, hydrogen gas, okay, that's no longer just hydrogen, it's H2. So it would be a compound, okay, or what we also call a diatomic element. It's a twinsy element. You won't find hydrogen by itself. It always partners with something else, including itself. To remember that, the diatomic elements, it's on your blue periodic table, but it's on the bottom of the first side of it. But remember this, Brinkelhoff. That's how we remember the diatomic elements. So all of these elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, they are the twinsy elements. They always are found in pairs when they're by themselves. Okay, J.J. Thomson's cathode ray tube. This was Unit 5. Okay, Unit 5. Prove the existence of negatively charged particles. Hopefully you know them by now. They are electrons. Okay, we have electrons, protons, and neutrons, by the way. Protons are positively charged, neutrons are negative. Protons and neutrons have a mass of 1, and electrons have 0 mass. Okay, and that's why when we talk about atomic mass, it's the protons and the neutrons added together. Okay, Rutherford's gold foil experiment proved that the atom is mostly empty space. Electrons are located orbiting the nucleus. A tiny dense positively charged area exists in the middle, and he called it the nucleus. Okay, so remember Rutherford, he was shooting alpha particles at a sheet of gold foil, and what was interesting is most of the time it went right through, but every once in a while, because the alpha particles would hit the nucleus, it would bounce off in random directions. And so Rutherford's molecule kind of looks like this, where there's a dense positively charged nucleus, and then you have the electrons kind of orbiting around, kind of like Big Bang Theory's logo. Okay, we have an isotope is an atom of an element that differs in mass due to a different number of neutrons. Remember that if we have a different number of electrons, it's called an ion. And then if we change the number of protons, we get whole different element. Okay, the mass listed on the periodic table is the atomic mass of all the different, and we can even say it's the average, okay, mass of all the different isotopes of the element by abundance. And so that's why they're decimal numbers. So for example, if we found all of the helium atoms in the universe, most of them have an atomic mass of 4, but every once in a while you have a helium with 5, atomic mass of 5. It has an extra neutron, and so we average them. And so because most of them have an atomic mass of 4, that's why it's 4.00260. But every once in a while you do get a helium atom with 5 atomic mass of 5 extra neutron. Okay, atomic number, okay, is the number that isn't a decimal, and it's the number of protons. Okay, so it's always a whole number. Atomic mass is the number of protons and neutrons in the atom. So if I wanted to find the number of neutrons, I would subtract the atomic number and the atomic mass. So for example, carbon is like 12.00 something something. Okay, so I would subtract 12 minus 6 to get 6 neutrons. It has 6 protons, and usually it has 6 electrons. Oh, and look, we have some practice problems of that. So consider atom with 33 protons, mass number of 75. Okay, so I'm going to add my periodic table here to help us out. Okay, so if I look at my periodic table, 33 protons. So looking for a 33, it'd be this guy right here. It's arsenic. Okay, so AS. How many? So it has a mass number of 75. So it's 75 over 33. So how many neutrons? I'm going to subtract those two to get neutrons. 75 minus 33 gives me 42. So it's 42 neutrons. How many electrons? It doesn't say that it's charged, so I'm going to assume it has the same amount as protons. Isotopic notation would be the mass number and then the element. And then the nuclear symbol would be AS. I already wrote it up there, but I'll write it again. 75 over 33. Okay. All right, so moving on. Silver 108. How many protons? Again, Ag, it would look like this. The nuclear symbol. And again, silver, I gotta look for it. Where's silver? Silver is right here. So 47 is 47, 1 and 107. So 47 has a atomic number 47. And actually, I'm going to copy this and move it down here. That's the nuclear symbol. Okay, how many protons does it have? It has 47. This shouldn't be protons, it should be neutrons, because we just asked that question. So neutrons would be 108 minus 47, so that would be 61. And then how many electrons? Again, it doesn't say anything about it being charged, so I'm going to assume it has a equal net charge of 0, so it's the same amount of electrons as protons. Okay, palladium. Palladium, PD 106. Again, I gotta look for palladium. Where is palladium? Right next to silver. Okay, palladium has 46 over 106. Okay, so it has 46 protons. Again, this is supposed to be neutrons. So 106 over 46 would be 60. 60 neutrons. How many electrons? Again, it's going to have the same since there's no charge. Isotopic notation would be PD 106. Okay. And you can write it that way or the other way. I wrote it over here the other way, but AS 75. Okay. All right. Good. Moving on. Okay, consider element X has 3 isotopes. So this is what we're talking about, that the mass is the average of all the isotopes. So we have one that's 125. So how do you find the average? So what I'm going to do is I'm going to do 125 times the percentage. So it's 0.15. Remember that 0.15 is 15%, not 1.5. Okay, so 15% would be 0.15. And add that to the next isotope, which turns out to be 127. Put some brackets. Okay, 127 times its abundance, so 0.75. And then add that to the third one, which is 128 times 0.1. Okay, I'm going to add all those together. So let's see here. I got 125 times 0.15 added to 127. Whoops, forgot the parentheses. Times 0.75 added to 128 times 0.1. Okay, and I get the grand total is 126.8. Okay, 126.8 is my atomic mass. So if I look on the periodic table, what is 126.8? Probably tellurium. Yeah, probably tellurium. Oh, 126. Actually, sorry, it's probably iodine. Okay, 126.9. Okay, remember that the periodic table is not ordered according to atomic mass. As you can see right there, iodine should be in front of tellurium if that were the case, but rather it is organized according to the amount of protons, the atomic number. Okay, so it's iodine. Okay, moving on along, units would be AMU, or grams per mole. Okay, atomic number for fluorine. So if we look at fluorine, atomic number, the whole number is 9. Okay, how many neutrons would a fluorine 19 have? So again, I subtracted 19 minus 9 is 10. The nuclear symbol for fluorine 19, which I just wrote to help me solve that problem. Okay. Okay, element has 30 neutrons, 26 electrons. What is Z? So by Z, I'm referring to A over Z. Okay, my atomic number. Okay, so notice there's no charge. So if it has 26 electrons, that means it has 26 protons. Okay, 26 protons. And if that's the case, and there's 30 neutrons, 26, since that's my protons, I'm going to add them together, that's 56 neutrons. Or sorry, 56 is my atomic mass, AMU. And if that's the case, 26 protons, what has 26 protons? That would be iron. Okay, iron has 26 protons. Okay, so we can use this to identify different atoms. Okay, moving on along, calcium atom. We're going to write the electron configuration. This was unit 6. Okay, calcium atom. So how do we do electron configuration? Let's add another periodic table so I don't have to keep scrolling. Okay, so remember that when we write electron configurations, we have to remember that this section is S, this section is P, this is F, and the transition metals are D. And then we have a couple numbers. So the first number is going to be the column it's in, and the second exponent number will be the column it's in. Okay, so when we're doing electron configuration, gotta remember that there's these regions, and then there's a big number and a small number. The big number is which row, which period it's in, and then the small number is which column it's in. And so for calcium, I have to fill up everything up until calcium, because calcium is a compounded atom that is basically everything up until that point plus one more proton and one more electron. And so I'm going to just kind of fill up rows as we go. And so I'm going to fill them up with a highlighter. when I get a chance. So fill up the first row, so hydrogen and helium. Again, I only have to put what is on the furthest right of that section. So that would be 1s2. Then I'm going to fill up this section, so 2s2. Then this row would be, all the way to neon, would be 2p6. And then sodium and magnesium would be 3s2. Aluminum to argon, 3p6. And then we can finally get to calcium, which would be 4s2. Okay, second atom in row 4 in the S area. Okay, if I were to write shorthand, you would just put the noble gas that is right above it, so argon, and then 4s2. Okay, orbital filling diagram, kind of the same thing. Instead of putting numbers, I'd put arrows. So 1s is filled up, 2s is filled up, and these arrows represent the spin of the electron. 2p, there's 3 different orbitals for a total of 6, that's why it's 2p6. Okay, 3s is filled up, 3p. Again, there's a total of 6 electrons. Each orbital can hold 2 electrons. And then finally we get 4s. Okay, the highest energy levels refer to which row it is. Highest energy level. So this one has the highest energy is 4. And how many valence electrons? Again, which column is it in? So calcium is in the second column to the left, so it has 2 valence electrons. 2 electrons on the outermost shell, which is this 4s orbital. Okay, silicon, we're going to do next. Just going to erase some of this. Okay, silicon. Again, I'm going to fill up the first row, so 1s2. Beryllium is 2s2. Fill up neon, up to neon, 2p6, and sodium, magnesium. And then silicon's right here, so it's going to be 3, row 3, in the p area, and it's the second atom in that area, so 3p2. Okay, orbital filling diagram. Okay, 1s is filled, 2s is filled, 2p, there's 3 orbitals, all filled, 3s is filled, and 3p, remember, Hund's rule, we have to fill up everything halfway first before doubling up. Okay, it's kind of like the bus rule. Okay, if there's an open seat, the electron's gonna take that open seat rather than pair up. Okay, so that would be the orbital filling diagram. And again, if I were to write the shorthand method for electron configuration, I'd write the noble gas right above, in the row above silicon, which is neon, and that covers all the way up to neon. So I just have to write 3s2, 3p2. Okay. Highest energy is 3. How many valence electrons? So again, which column is it in? We're going to skip the transition metals for valence electrons. So 1, 2, 3, 4. Okay, we have, given the opposite, we're given the electron configuration. Notice it's 4s1, so it's in row 4. 1, 2, 3, 4, and it's the first one, so it would be potassium. And it would have 1 valence electron. Okay, 1 electron in the 4th row. 5 valence electrons in the 3rd energy level. So 3rd energy level would be row 3. So it's somewhere in this row. Row 3, and has 5 valence electrons. So 1, 2, 3, 4, 5. It is phosphorus. Okay, its electron configuration would be 1s2, 2s2, 2p6, 3s2, and then 3p5. 5 valence electrons, 3p3 actually. It has a total of 5 electrons in row 3. Okay, or it's in the 5th column, same thing. Orbital diagram. Filling up all of the orbitals. And again, 3p, I gotta fill up everything halfway first before doubling up. Okay. All right, so that's unit 5 and 6. We're kind of going backwards into unit 3 and 4, which is moles and stoichiometry. So moles, remember that a mole if I draw my mole heart, okay, mole, the mole is really useful because we can use it to calculate grams, in which we use the molar mass. We either divide or multiply by the molar mass. We can get it into particles, so like molecules or atoms. We use Avogadro's number, 6 times 10 to the 23rd. Again, we multiply or we divide by that number to get particles. And then we can also get particles of a gas, or sorry, volume of gas. Okay, volume of a gas, or liters of a gas, using 22.4. Okay, again, when we go towards the heart, we need to divide. I like to think of, if I wanted to get to my physical heart, you'd have to divide the skin and cut open the skin to get to the heart, to get to the mole. And then if I wanted to go away from the mole, you're gonna have to multiply. So in this case, I have 7.2 grams of vanadium. And so I'm starting off with grams, which is here, and I want to get moles. So I'm going to and actually have it backwards here. Whoops. To get to it, I'm going to times and get back to moles, divide by mm, molar mass, which is on the periodic table. So I'm going to get my periodic table out again. All right, periodic table. And vanadium, so again, is going to be grams over moles. Okay, how many grams? I'm going to look for grams of vanadium, so 50.94. Okay, so that's going to be 7.2 divided by 50.94, which is equal to 1.4 times 10 to the negative 1 moles of vanadium. Okay, next one, 0.82 moles of fluorine. Okay, fluorine. So if I have 0.82 moles of it, moles on bottom, grams on top. Okay. Now remember, the thing about fluorine is actually F2. So when I look at fluorine, 19. Okay, 19 grams for every 1 mole. But I'm going to have to multiply that by 2 because there's 2 fluorines. So 19 times 2 is 38. So this should be 38. 38 times 0.82 gives me 31.2 grams of fluorine. Okay. Remember that the diatomics are Brinkelhoff. Okay, fluorine is at the end. Okay, molecules, so 143.0 grams. I want to get grams into moles, and then moles into molecules, which is not the same thing. Okay, the moles are 1. Okay, and it's disulfur. So S2, disulfur trioxide, so S2O3. So I gotta find the molar mass of S2O3. Sulfur is 32 and oxygen 16. So it's gonna be 32 times 2 added to 16 times 3 for the molar mass. So that's 64 added to, is that 48? Okay, so I get 112 grams. Okay, and then to get molecules, I'm going to use Avogadro's number. Okay, so let's see, 143 divided by 112 times by 6e to the 23rd. I got a huge number because it's a number of molecules, 7.66 times 10 to the 23rd molecules of S2O3. All right. Okay, next one, 0.050 moles of CO2, carbon dioxide. I want molecules. So again, whatever you want to cancel out goes on the bottom, since I have moles, and then I want molecules. So I'm going to use Avogadro's number again, 1 mole. So let's see, 6E23 times by 0.05. Okay, 3 times 10 to the 22 molecules of CO2. Okay, grams of nitrogen trichloride. Okay, tri is 3, so NCl3. I have 2.90 times 10 to the 25 molecules of it. So again, molecules goes on bottom. I want grams, so first got to get into moles, and then once I get into moles, I can get into grams. Okay, so in 1 mole, there's 6 times 10 to the 23rd molecules. And then again, got to find the molar mass of NCl3. So N is 14, Cl is 35.5 right here. Okay, so 14 plus 35.5 times 3. Give me the molar mass. So 35.5 times 3 added to 14. Okay, so what is that? 120.5. 120.5. So 2.9 e to the 25 divided by 6 e to the 23rd times by 120.5. That's going to be equal to 5.82 times 10 to the 3rd. 5.82 times 10 to the 3rd grams. So that's like 5,000 grams of it. Okay, of nitrogen trichloride. Okay, great. 1 mole of bromine, how many grams? So again, bromine is a diatomic. So in 1 mole of it, how many grams of it do I have? If I look at bromine, bromine is right over here. So 80, 79.9, you can just round to 80. So, but there's 2 of them, since bromine is Br2, so 160. And 1 times 160 is just going to be 160 grams of Br2. Okay, how many moles are in 5.08 times 10 to the 21 molecules? So molecules, moles, 1 mole per every 6 times 10 to the 23 molecules. So just divide them. Let's see, 5.08 E21 divided by 6 E23. Okay, 8.46, 8.47, 10 to the negative 3rd. What did it say? 8.47. 10 to the negative 3rd. Yeah. Okay. And moles. Okay, how many moles are there in 8.3 grams of lead? Lead is Pb. Okay, so we're going to look for lead. Lead is right here, 207.2. So 8.3 divided by 207.2. Okay, which would be 4 times 10 to the negative 2 moles of lead. Okay, molar mass of the following compounds. So let me get a new periodic table. Let's put it in this little corner up here. Okay, so NaOH, Na, we have Na over here, O and hydrogen, so 23, 16, and 1. Yeah, 23 plus 16 plus 1 would give us the molar mass. So that is 40, right? And just do it 23 plus 16 plus 1. Yep, 40 grams per mole. NaCl, Na was 23. Cl is over here, 35.5, which would be 58.5 grams per mole. Okay, water, hydrogen is 1 times 2, added to 16, so that's 18 grams per mole. Okay, carbon dioxide, let's see, carbon is 12, oxygen is 16. So 12 plus 16 times 2, so 32, 44 grams per mole. Cl2 is that diatomic that we've been, and again, diatomics are over here on your blue periodic table. So don't even have to memorize it. Chlorine is 35.5. So 35.5 times 2 would give us 70.1. Or is that 71? 71 grams per mole. And our last one, big one, Fe2SO3. So Fe is 55.85, so we'll do 56. 56 times 2 added to, remember, since there's parentheses, this 3 applies to both the S and the O, 4, so there's 3 S's, so 32 times 3, and then added to 16 times 3, since that 3 multiplies is 12 oxygens. Alright, so I'm going to get my calculator again. 56 times 2, added to 32 times 3, added to 16 times 12, 400 grams per mole. Okay, so that's how we find the molar mass, so that we can use that for calculating our moles. Okay, continuing on. Okay, we have converting into moles, so 4.35 times 10 to the 24 molecules, and converting to moles, so moles, dividing it by 6 times 10 to the 23rd. Whenever it's molecules or particles or atoms, that's the number we use. 4.35, 24 divided by 6e23 would give us 7.25. Okay, so that would be 7.25 moles of chlorine. Okay, and let's see. Next one is krypton. 5.62 grams into moles. Again, since it's grams, we got to find the molar mass. So krypton is over here. 83.6. 83.6. 5.62 divided by 83.6. Okay, so that's equal to 6.7 times 10 to the negative 2 moles krypton. Box my answers a little bit more neat. Helium gas, 71.7 liters. Remember, it has to be liters of a gas, not liters of a liquid, in order to use 22.4. There's always, it doesn't matter what kind of gas it is. That's kind of the cool thing. As long as it's a gas, 22.4 liters of it will be 1 mole. 71.7 divided by 22.4, so 3.2 moles of He. Okay. 9 times 10 to the 21 atoms of carbon. So atoms into moles would be Avogadro's number. So let's see, 9e21 over 6e23, 1.5 times 10 to the negative 2 moles of carbon. Okay, 3 grams of sodium hydroxide, so grams of NaOH. So NaOH we found up here, which is 40. We found it up here already, so I'm not going to calculate. Just adding up Na plus O and H. So 3 divided by 40 is 7.5 times 10 to the negative 2 moles of NaOH. 4 liters of hydrogen gas, 0.4 liters. Again, it's 22.4. As long as it's a gas, 0.4 divided by 22.4. 1.79 times 10 to the negative 2 moles of H2. Okay, conversions. So just kind of doing the same thing. 2.1 times 10 to the 24 atoms. So atoms goes on bottom. We want grams. I'm just going to put grams on top to simplify it, but you know what? I'm just going to... We should do it like this with the moles and moles, but technically moles cancel out. So you could just put grams over the atoms. Save you some time. So since it's lithium, gotta use your periodic table. So let's see, I'm gonna put another periodic table. Put a lot of periodic tables on this. I'm gonna put it over here. Okay, so lithium is over here. So what is that? 6.9, so 7. 7, so let's see. 2.1 e to the 24 divided by 6 e to the 23 times 7 would be 24.5 grams of lithium. Lithium's a hot commodity nowadays. We need it for our batteries. Okay, next one, 29.1 liters of O2. So liters over grams. Again, I'm going to combine steps. You should have this mole over mole, but I'm going to combine steps. So oxygen, over here it is 32. Or sorry, 16, but there's 2 of them. So 32 and 22.4. So 29.1 divided by 22.4. 32. Okay, 41.6 grams of O2. Okay, next one. Okay, we have 4.44 times 10 to the 22 molecules. So molecules goes on bottom. Ooh, it's so small. Liters goes on top, 22.4, 6 times 10 to the 23rd. So let's see, 4.44 e to the 22 divided by 6 e23 times 22.4 equals to 1.66 liters of HCl gas. Okay, next one, ammonia. 14.45 grams over liter. I want it into liters. 22.4 grams of NH3. So N is over here, hydrogen is up there. So N is 14 plus 1 times 3. There's 3 hydrogens, so 17. Okay, that's going to be equal to 14.45 times 22.4 divided by 17 is 19.04 3. Okay, next one, 3.36 liters. Liters, molecules goes on top. Whoop. 6 times 10 to the 23rd and 22.4. So let's see, 3.36 divided by 22.4. Multiplied by 6e23 gives us 9 times 10 to the 22, which makes sense as a big number because we're talking about molecules of N2. Okay, for this next problem, 272.8 grams of silver nitrate to molecules. So Avogadro's number. Okay, AgNO3, let's see. Ag is 108 added to nitrogen, which I think is 14, yep. And then added to 3 oxygens. Oxygen is 16. So let's see, that would be 108 plus 14 plus 16 times 3, 170. Okay, so 170. So let's see, 272.8 times 6e23 divided by 170, 9.63. Okay, of AgNO3. Alright, great. Okay, mass percent. So whenever we have a percent, we take whatever we're making a percentage of and divide it by the total. So for potassium carbonate, I need to find the total first. So let's see, carbon is 12, oxygen is 16, there's 3 of them, and then potassium is 39. So 39 times 2. So let's see, what is that? 39 times 2, added to 12, added to 16 times 3. Okay, so 138. So I'm going to divide each of these guys by 138. So 39 times 2. So which is 78. So the percentage of potassium would be 78 over 138. Carbon would be 12 over 138. Oxygen would be 48 over 138, which 16 times 3 is 48. Alright, so calculate that. 78 divided by 138 is 57%. 0.57 is 57%. Okay, 57. Carbon is 12 over 138, so that's 9%. And then 48 over 138. Or you could just add up those two, subtract by 100, but 35, okay, 35%. Okay, so that's mass percent. Okay, we have 31 liters of ethanol. How many molecules of that? And the density is given, so we're probably gonna have to use that because this is a liquid and not a gas. So I gotta use D equals M over V. So the density is 0.789 grams per milliliter. That's equal to, I'm trying to find molecules, so I'm gonna have to get into mass. 31 liters is 31,000 milliliters. Okay, so I'm cross multiplying m times 1 and 31,000 times 0.789. 0.789 times 31,000. So 2.45 times 10 to the 4th grams. Next I want moles, and then of course I'm going to skip a step and just put molecules. But I could put 2 conversion factors. I'm going to squeeze into one. Okay, got to find the molar mass of this guy, of C2H6O, to get my grams. So carbon is 12, hydrogen is 1, and oxygen is 16. So what is that? 24 plus 6 plus 16. 46 grams per mole. So 46. So I'm going to do that 2.45 to the 4th divided by 46 times by 6e23. And we get 3.2 times 10 to the 26 molecules of ethanol, C2H6O. Okay. Okay, let's see. Compound is made out of that much. What is the empirical formula? Okay, so we didn't cover this in our year, but I'm just going to show you how to do it anyways. So we're trying to find the empirical formula, which is the simplest formula for this compound with aluminum and oxygen. So we have 37.8, and this is aluminum. Oxygen is 33.6. What I'm going to do is get them into moles to get a mole percentage. So aluminum, if you look at the periodic table, is 27. So 27, and then oxygen is 16. So that's what I'm going to do first. So let's see, 37.8. 37.8 divided by 27. Go to 1.4, and then 33.6 divided by 16, 2.1. I'm going to divide both by whatever the smallest number is. In this case is 1.4, so this is 1, and 2.1 divided by 1.4, whoops, is equal to 1.5. However, you can't have 1.5 atoms of oxygen, so I'm going to multiply them both by 2 to get them into a whole number. So it's going to be, there's going to be 2 aluminums and 3 oxygens. That's empirical. Okay, the next problem is another empirical formula. So I'm going to write carbon, we have 24.3. If it's percent or grams, we can do the same method. H is 4, chlorine is 71.7. Okay, so we want to find empirical formula and then molecular formula. So I'm going to divide them by the molar mass. Carbon is 12, hydrogen is 1, chlorine is 35.5, I believe. Let's check on that. Yeah, 35.5. So let's see, what is that equal to? 24.3 divided by 12 is 2.025. We got 4, and then 71.7 divided by 35.5, 2.019. Again, divide by the smallest number. Okay. So it's going to be C1H2Cl. That's the empirical formula. Next, we have to find the molecular formula. Empirical formula is the simplest form. And so first I'm going to find my molar mass. Okay, so let's see, we have 12 plus 2 plus 35.5. So that gives us 49.5. So that is our molar mass of the empirical formula. We're going to take 198 and divide it into the 49.5. And that gives us 4. Oops. So I'm going to multiply all of it by 4. C4H8Cl4, that is my molecular formula. Okay, the next problem, we have chlorine. How many chlorine atoms in 1 mole of copper 2 chloride? So copper 2 chloride means that the charge of copper is +2, and so that means that there's 2 chlorine molecules, or 2 chlorine atoms. So we have how many chlorine atoms are in 1 mole of that. So 1 mole. So 1 mole, we want to cancel out moles, and we want molecules. So use Avogadro's number. So let's see, that turns out to be 6 times 10 to the 23rd molecules. Of course, we don't want molecules. So in every molecule, we have to ask ourselves how many chlorine atoms. And notice, if there's one of these molecules, there's 2 chlorine atoms. So basically, we're multiplying that really big number by 2. So we have 6 to the 23rd times 2. So we get 1.2 times 10 to the 24th chlorine atoms. Okay. Notice we want the same. How many moles of chlorine atoms are in 3 moles of copper 2 chloride? So what we're going to do is start off with 3 moles this time. Okay, 1 mole. Okay, and we want, and actually, since it's basically the same problem as the first problem, we're just going to multiply 3 times what we got initially. And actually, sorry, no, never mind. We want moles of chlorine atoms. So what I'm going to do is kind of do the same thing. 1 mole, 6 times 10 to the 23rd molecules. That gives 6 times 10 to the 23rd molecules. We want to find how many chlorines. So Cl, 1 molecule, which is equal to what we just got. And then the last step is we want to find how many moles of that. So if I have this many atoms in 1 mole, I have 6 times 10 to the 20th, oops, wrong one. That goes on the bottom, 6 times 10 to the 23rd in 1 mole. So I'm just going to take that number that we just got and divide it by 6e23. So I'm going to have 2 moles chlorine atoms and 3 moles of copper chloride. Actually, and I totally forgot, I'm sorry, I made a mistake. 3, I forgot to multiply the 3 at the beginning. So this needs to multiply by 3. 6e23 times 3 times 2 divided by 6e23, and you might already be able to predict the answer. Okay, we're going to get 6 moles of chlorine atoms. So it's just double whatever we started with. And that makes sense. If we have 3 of these molecules, then 3 times 2 is 6. Okay, how many moles of chlorine atoms are in 269 grams? So we have 269 grams of copper 2 chloride. I'm going to get it into moles. So in 1 mole, let's see, the Molar mass of copper is 63.5. 63.5 added to 35.5 times 2. That's chlorine. And that's going to be equal to 63.5 added to 35.5 times 2. 134.5. So 134.5. Okay, but then, okay, I'm gonna just put it all in the same equation. So for every mole, there's 6 times 10 to the 23rd molecules. And for every 1 molecule, I have 2 chlorine atoms. And then I'm gonna take my chlorine atoms and divide it into 1 mole again. 6 times 10 to the 23rd. Sorry, that's kind of messy. 6 times 10 to the 23rd atoms in 1 mole. So honestly, these guys cancel out, but I'll just do it out for you folks. 269 divided by 134.5 times 6e23 times 2 divided by 6e23. Okay, we get 4. 4 moles of chlorine atoms. Okay. Alright, so that's unit 3 for you folks. I'm gonna go to naming next, unit 1. So we're going to give the correct formula for these guys. So the first one's carbon dioxide, which is easy. CO2, diphosphorus, phosphorus is P, so 2P. And pentoxide, so 5 oxygens. Okay, silicon dioxide, sulfur dioxide, iodine trichloride, dinitrogen trioxide. Okay, 2 nitrogens, 3 oxygens. I'm going off of the prefixes, by the way. Carbon monoxide, di is 2, mono is 1, carbon tetra is 4, penta is 5, and oxygen is 3. Okay, in this problem, we're going to have to go backwards and give the name. So here's how we do that. I'm going to give my periodic table. Alright. Yes, help me out a little bit. So just as a refresher, here's how we name the different atoms. I'm going to draw my staircase. Okay, so these are the non-metals. Everything else is a metal. Okay, just as a reminder, if we have non-metal to non-metal, we use prefixes. If it's a metal to non-metal, we can just name it. But if we're coming up with a formula, the charges have to balance. Okay, the charges have to balance. So this one is N and O. Notice N and O are both nonmetals, and so it is what we call a covalent compound versus an ionic compound. So we use prefixes. So N2 is dinitrogen, and 4 is tetroxide. Okay, same thing here. NO, they're both nonmetals. So it's nitrogen. We don't have to write mononitrogen if it's the first element there. Nitrogen monoxide. Okay, next is As2O3. Again, As is a nonmetal. Okay, and As is arsenic. So diarsenic pentoxide. Okay, next one, carbon. Carbon and chlorine are also in the nonmetal section, so carbon tetrachloride. Okay, Se is selenium. So let's see, selenium is in there, F is in there, fluorine. So selenium hexafluoride. Okay, actually all these look like they're turning out to be nonmetal to nonmetal. Sulfur and oxygen are both nonmetals, so sulfur trioxide.
No, she's not.
Okay, the next one is nitrogen, and 2 oxygens would be dioxide. Okay, nitrogen and oxygen. Phosphorus is over here, and chlorine is 2 nonmetals, so phosphorus trichloride. And then lastly, hydrogen technically is a nonmetal. You got to remember that, even though it's not with all the rest over here in the top right. So it's dihydrogen monoxide, the official name for water. Okay, dihydrogen monoxide. Okay, moving on. Now we have a mixture of ionic and covalent compounds. Okay, so again, how do you tell? Well, if there's, let me draw another periodic table over here. Okay. If they are not, if it's 2 nonmetals, it's covalent. If it's a metal and nonmetal, it's ionic. So notice sodium and fluorine, there's 1 metal and 1 nonmetal, so it is ionic. As and N are 2 nonmetals, so covalent. Okay, KClO3, and actually we should practice naming some of these since we didn't have really any ionic practice, which ionic compounds are really easy, you just name them, no prefixes, so sodium fluoride. Okay, the next one is AsN3, so again 2 nonmetals, so triarsenic pentanitride. Okay, next is KClO3. So KClO3 is a polyatomic, and it has a charge of -1, so it would be considered a nonmetal. Potassium is a metal, so it's an ionic compound. This would be potassium, and then you got to look on the back of your periodic table for KClO, right? If you look at the back of your periodic table, which I'll put it down here. Okay. You look on the back, right down here, we have KClO right here, so it's chlorate, potassium chlorate. Again, you don't need prefixes because it's an ionic compound. Okay, CdO, CD, cadmium, is right here. So notice cadmium and oxygen. Okay, cadmium and oxygen, it is an ionic compound, and it's a transition metal. So how would I name that? Well, I'd put cadmium, and then it needs to have a Roman numeral that tells me the charge of the cadmium. And so how do I do charges? Well, remember at the top of the periodic table, I have these charges. So if I look at oxygen, it's -2. So that means cadmium has to balance it out to +2. So cadmium is cadmium-2 oxide. Again, no prefixes because it's an ionic compound. Okay, next we have silicon. Okay, silicon, which is over here, and chlorine. So it's a covalent compound. So silicon tetrachloride. Okay, CrO, Cr is over here, oxygen is here, so it's an ionic compound. Chromium is a transition metal, there's no charge above it, so it's in this block, right? Transition metals are all over here. So chromium needs a Roman numeral, so I gotta look at charge of oxygen, which is -2. There's 3 of them, so -6. So chromium has to be 6. So I'm going to write Roman numeral 6. Chromium 6 oxide. Okay, next one is SnCl4. So Sn is, let's see, over here. Okay, Sn is tin. Chlorine is a nonmetal, so it is an ionic compound, metal and nonmetal. So I'm going to write tin. Chlorine is -1 charge, but there's 4 of them, so tin has to be +4. So I'm going to write Roman numeral 4, chloride. Okay, next one, AgH. So Ag is silver. It is a metal. Hydrogen is the nonmetal. So it's going to be silver. Silver is a transition metal, needs that Roman numeral. In this case, it's a really unusual compound. Hydrogen is going to be the negative component. So it's going to be, silver is going to balance that out. So silver 1 hydride. Okay, usually hydrogen is +1, but in this case it's an exception. Okay, next CuOH. OH is a polyatomic. Cu is copper, which is a transition metal. Okay, Cu is right here. Okay, so copper. So this is ionic. Other one is ionic. Okay, whenever you have two opposite charges, that's another way you can tell it's ionic. Right? Arsenic is supposed to be -3, and so is nitrogen. So you can tell that it's not ionic. The charges don't balance. Okay, copper, OH. We're going to look on our back of our periodic table. OH is hydroxide. There's a charge of -1 in that little corner right there. Right there is a -1. So -1, copper has to be +1. Copper 1 hydroxide. Okay, next Mn. Manganese is a metal. Basically, if you have at least one metal, it's going to be ionic. That's another way to put it. So manganese. PO4 is phosphate with a -3 charge. So -3, there's 2 of them, so -6. Manganese has to be +6. Phosphate. Okay, the next one, SO3. Notice S and O, they're both nonmetals, so it is covalent. So we're going to use prefixes. Sulfur trioxide. Next, AuBr. Au is gold. It's a transition metal. We look at Br is a -1 charge. So gold is going to be 1. Gold 1 bromide. Okay, transition metal, so you need the Roman numeral. Alright, so that's how to name some of these compounds, and remember that transition metals, you need those Roman numerals. If you have something in this area, or like even aluminum, you don't need to, you have the charges there for you, so you just swap and drop them, right? So if I have, for example, calcium chloride, I think I did this example before. Okay, you write the elements, you look at their charge. Calcium is +2, chlorine is -1, so we swap and drop them. So we need 2 chlorines, 2 -1 charges to balance out that +2. Okay, so if we're going from name to formula, you gotta swap and drop for ionic compounds. Okay, moving on to Unit 8, bonding and Lewis dot structures. We're gonna draw some of these shapes and name at least one example. So linear is, and you're gonna have the chart, the Vesper chart on your test, so you don't have to memorize all of these. But a really good example of a linear molecule would be N2. Okay, remember, how do you draw these guys? Well, so if I have nitrogen, let me add another periodic table. Okay, nitrogen is up here. Okay, and so I gotta count how many valence electrons it has. Remember, it's just however many columns to the left you are. The max is 8 valence electrons. So nitrogen's column is 5. So 5 plus 5, there should be 10. So what I'm gonna do to draw it, so I'm gonna single bond them, put valence electrons. I'm gonna count 2, 4, 6, 8, 10, 12, 14. I have 14, that's too many. I'm supposed to have 10. So what I'm going to do to fix that is I'm going to erase two what we call lone pairs of electrons, and then recount. Okay, I'm going to recount them. So I'm going to erase 2 and draw a line, draw a double bond. And then recount 2, 4, 6, 8, 10, 12. That's still too many. So I'm going to erase one more set of 2 more lone pairs, one from each of the atoms, and add a triple bond. 2, 4, 6, 8. 2, 4, 6, 8, 10. So now this is the correct drawing for N2. Okay. And it's linear because there's only 2 atoms. Any molecule with only 2 atoms is going to be linear. Okay, and remember that we also kind of talked about polarity, which the way to tell if it's polar or not is by if it has symmetry, right? So if I take this guy and I rotate it, let's see if I can rotate it. Rotate it 180 degrees, is it the same thing? And yeah, it is. I mean, it's written upside down, but it's still nitrogen with 2 lone pairs. So this has rotational symmetry, so it would be nonpolar. Oops, it would be nonpolar. Okay, and the shape would be linear. Okay, for tetrahedral, a good example is CH4. Again, I'm gonna count how many valence electrons. So carbon has 4 valence electrons. Okay, carbon is right here for your reference. Hydrogen has 1 valence electron. So 4 plus 4 should have 8 valence electrons. So I'm gonna bond carbon, bond everything to carbon. Remember, hydrogen only has a bond. You don't need to fill it up with lone pairs. Then I'm gonna count 1, 2, 3, 4. Okay, sorry, 2, 4, 6, 8. 8 electrons. So it matches this number, so don't have to add double bonds. Okay, so tetrahedral, I have one thing that's bonded to 4 other things. Again, if I rotate this 180 degrees, it's the same thing. And so this would be nonpolar. Another way to tell if it's polar is if it has a lone pair on the center, which this one doesn't, so it's still nonpolar. Okay, pyramidal. Okay, trigonal pyramidal is if I have something with, something that's bonded to 3 things with a lone pair. Okay, so a good example of this would be NH3. Okay, again, N has 5 valence electrons plus 1 times 3, should be 8. So I'm gonna bond the hydrogens, and then since nitrogen has an open spot right there, I'm gonna fill it up with valence electrons, or a lone pair, and then count 1, 2, 3, 4, 2, 4, 6, 8. Okay, so that's 8. So that matches, so that's my Lewis dot structure. Okay, and notice since it has a lone pair on the central atom right there, it is going to be polar. Okay, bent. A good bent molecule is H2O. Again, I'm going to add up my valence electrons for oxygen is 6. So I'm going to do that, fill up the center atom with valence electrons and double check. 2, 4, 6, 8. Okay, so that's how much I'm supposed to have. Okay, notice this would not be tetrahedral because it doesn't have 4 bonds. It has 2 bonds and 2 lone pairs. So this is going to be a bent molecule. And since there's lone pairs on the center, it is going to be polar. And lo and behold, water is polar molecule. Okay, then we have trigonal planar. Trigonal planar is when it has bonded to three things, no lone pairs. So a good example of this would be BH3, boron trihydride. Boron has 3 valence electrons, plus hydrogen's 3 should be 6. Okay, so this is one example of something that doesn't fulfill octet. The octet rule, oct is 8, so it doesn't have 8 valence electrons around it, which is fine. Okay, so boron trihydride, again, to tell polarity, let's see if I can rotate it, and I can, right? If I rotate it, what is that, like 60 degrees or something like that, then it's the same thing. So this would be nonpolar. Okay, so those are the main shapes that you'll have to know for the final exam. Of course there's more, but you will only be responsible for those on the final exam. Okay. Okay, on to the next question. Discuss the differences between ionic and covalent compound. So we kind of already mentioned that an ionic compound is a metal bonded to a nonmetal. Covalent is nonmetal to nonmetal. So for ionic, because it's a metal which is positively charged and nonmetals are negatively charged, they are charged what we call electrostatically, or their charges hold them together. Opposite charges hold them together. For covalent, their charges are both negative. So it's not the charges that hold them together. Okay. And actually, it all has to do with electrons. So for positive and negative, remember that all atoms want to become like noble gases. They want to have a filled up orbital. They want to have 8 valence electrons. So what ends up happening is that the nonmetal gives electrons to the metal, or sorry, opposite way. The metal gives electrons to the nonmetal to become like a noble gas, and the nonmetal receives it, and that causes them to have charges. So for example, if I have sodium and chlorine, right, chlorine has 7 valence electrons in column 7. Sodium has 1 valence electron, and so they're both happy if sodium gives that electron to chlorine, but in doing so, sodium becomes +1 because it lost an electron. Electrons are negatively charged, and chlorine becomes -1, and that charge difference holds them together. So what happens there is that there's a transfer of electrons, and that's how we get redox reactions. Okay, transfer of electrons. For nonmetals, so for example, we have N2, okay, nitrogen. Nitrogen has 5 valence electrons. And so what ends up happening is that they both share electrons. These 3 lone electrons, they share them between both of them, and it counts for both of them. And that becomes a triple bond. So they share electrons. Okay, the rules that molecules follow in order to bond, they follow what we call the octet rule. Oct means 8, and so they want 8 valence electrons, just like the noble gases. And they do that because noble gases are very stable. Chemically speaking, they're very stable. And so they're going to either share electrons or donate electrons or take electrons in order to become like noble gases. What are the diatomic molecules? Brinkelhoff, kind of mentioned that earlier. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. These molecules will always be linear because there's only 2 of them. They're twinsy elements. Okay, single, double, triple bond. So single, double, triple bond. Triple bonds are the strongest, and they're also the shortest in length. Shortest in length. Single bonds are weakest, and they're the longest bond. double bonds are in the middle. So an example, H2 is a single bond. We got, what else is a double bond? Oxygen is double bond, and nitrogen is a triple bond. N2 and O2. Okay, balance and classify the type of reactions. This was unit 1. There are 5 different types of reactions. So we have magnesium with O2, and it produces magnesium oxide, MgO. Okay, so notice it's A plus B. You're combining them together, you're sticking them together to make something, and so that's a synthesis. Okay, you're making something. Aluminum with fluorine, remember fluorine is a diatomic, it produces aluminum fluoride. -1 plus 3, so 3. That's also synthesis. Potassium chlorate into potassium chloride and O2. So notice you have something, you start off with something and it breaks apart into 2 pieces. That's the opposite of synthesis, so decomposition. HCl and calcium to produce H2 and calcium chloride. So notice in this one, chlorine is initially with hydrogen, but it swaps with calcium. And so this is called a single swap or single displacement. Okay, next one, C3H8 plus O2. We have propane, gives off CO2 and H2O. So notice we have the 3 heads of the apocalypse. 3 necessary ingredients and products of fire. Combustion reactions will always have O2, CO2, and H2O and some kind of carbon compound. So this is combustion. We're burning. Oxygen is kind of like burning. We need it to burn stuff. Okay, next one, iron 3. So 3 means it has a plus 3. Chloride. Gonna swap and drop. Plus sodium hydroxide. Hydroxide is on the back of the periodic table, polyatomic. And it makes sodium chloride and iron 3 hydroxide. Okay, hydroxide is -1 charge. Okay, just gonna balance everything to make sure it all balances out. Okay, if it's not balanced, you gotta swap and drop. So notice in this case, iron swapped with sodium is a double swappage. You have 2 complete partners that are dancing together if we were to compare it to dancing. So this wouldn't be double, this wouldn't be single displacement, but rather double displacement. Okay, we didn't really cover net ionic equation either, and it won't be on your tests, but let's just do it. Barium nitrate, -1 plus 2, barium is plus 2, with sodium sulfate. Sulfate is SO4 to form barium sulfate. And sodium nitrate. Now notice keyword is precipitate, so that means that this is solid, the rest are aqueous. Okay, and so this was one of those things that we added 2 solutions together and it turned cloudy or it turned different color, and there's, chunks inside of there, solids precipitated. For net ionic, what we do is we cross out anything that doesn't pertain to the solid. So if we're to break up and cross out all of the ions that don't relate to barium sulfate, our net ionic equation would look something like this. BaSO4. It's going to be solid. Ba and SO4 are going to remain. So Ba plus 2 and SO4 minus 2. That's it. Okay, we cross out the NO3 and the Na because Yeah, we don't need them. And actually, forgot to balance it. So Na2. So we need a 2 here. Okay, but that doesn't affect our barium. If there was a 2 here in front of barium, I'd have to continue that 2, but that doesn't happen, so it doesn't matter. Okay, so that's our net ionic equation. Okay, another one. Magnesium reacts with HCl to form hydrogen gas and magnesium chloride. Okay. So that's our equation. Okay, next one. Lead to nitrate. Okay, lead is +2 -1. Ammonium is up here, is a polyatomic NH4 on the back of your periodic table. Okay, and it makes PbCl2. Plus, what is other players? Outsides and insides. NH4NO3. So again, this is a solid, so that's the only thing we're concerned with. So PbCl2. So, and we forgot to balance it, so there's 2 Cl's, so this should be a 2 here, 2 here, and a 2 here. Oh, wait, no. I'm doing something wrong here. Oh, it's supposed to be a 2 here, swap and drop. So, 2 there, good. Okay, so cross out everything that doesn't pertain to PbCl2. So Pb is going to remain +2, and Cl, which is going to be 2 Cl's because that 2 applies to both of them. Okay. Aqueous and aqueous. Okay, and then moving on, we're going to be doing these. So this, since it breaks apart, is a decomposition reaction. Okay, this next one. Okay, since it breaks apart into ions, it's a double displacement. So insides and outsides pair up. So NaNO3 and AgCO3. So this would be a double displacement. Okay, next, notice we got some burning going on. The products are always H2O and CO2. And actually, I totally forgot to balance these guys. So 2 and 2. Gotta make sure that there's equal amounts on both sides. This one we're gonna balance. So let's see what is not balanced. Carbons are not balanced. So I'm gonna do a 4 here. Hydrogens not balanced, so 4 there, and then lastly oxygens, so 8 oxygens here, 4 oxygens here, 12 oxygens, so 6, and this is going to be combustion. Okay, Na plus Br2, they're going to combine to make NaBr, -1 + 1. I'm going to balance this. This is a synthesis because we're adding 2 things together. Okay, next one, we got a double player, double dancers. So outside ZnPO4. Remember that the positive cation always goes first. And then lithium nitrate. PO4 is -3 on the back of your periodic table. And then notice this Zn, since NO3 is -1 on the back of your periodic table, there's 2 of them. This zinc is zinc 2. So that charge is gonna continue on. So we get Zn3PO4, and then to balance this guy, there's gonna be a 2 here, 2 PO4s, and 6 lithiums. This is double displacement. Okay, last one. I see right away there's a carbon compound with oxygen, so it's going to be combustion. So we're gonna do a 6 here, and then 7 here. But notice that 7 is gonna make an odd number of oxygens, which I cannot have. So I'm gonna double that to 14. Okay, so 14 oxygens plus 12 is 26. So 13. Okay. Alright, the next part is Unit 2, gases. We're going to do conversions. This is on your blue periodic table, on the back of your periodic table. So let me get that for us. Okay, so on the back of your periodic table, let me put it up here since we're done with this part. Okay, on the back of your periodic table, we have the conversion factors for gases up here that we will be using. And so 1.34 atm atmospheres, converting it into torr. So notice torr is 760 torr per 1 atm. So we're just multiplying it by 760. We get 1018 torr. Okay, torr to kPa. Okay, torr to kPa. So 101.3 and 760. So I'm going to do 784 times 101.3 divided by 760. That would give us 104.5 kPa, kilopascals. Okay, temperature unit. And that is also on your periodic table, right over here. Okay, to switch from Kelvin to Celsius, we just add 273. So that equal to 375 Kelvin. Okay, same thing here. 398 Kelvin. Okay, 695 mmHg, millimeters of mercury to atm. 1 atm, mmHg is 760, just like torr. So let's see. 695 divided by 760. So get a 0.91 atmospheres. 453 kPa to atm. kPa is 101.3. So 453 times 1 over 101.3. 4.47 atm. Okay, and then going backwards from Kelvin to Celsius. 350 minus 273, 42 Celsius. Remember that Celsius can be negative, but Kelvin cannot. 41. Okay, Kelvin, Lord Kelvin developed his scale so that there wouldn't be any negative numbers. Okay, and then the gas laws. Remember that we also have the gas laws on your periodic table. Right over here, combined gas law, we have ideal gas law. And from the combined gas law, we can get all the other gas laws. So that's kind of the nice thing about it. So I'm going to rewrite it over here. And if one of the variables is not mentioned or it stays constant, we can just ignore it. So we have carbon dioxide gas volume is 6.92 liters at 79.2 kPa. Okay, so that's pressure and volume. Notice that temperature is not mentioned, so we can ignore temperature. We're looking for pressure 2, pressure in kPa if the volume goes to 4.18 liters. Okay, so I'm going to solve for P2. Divide by 4.18. Okay, so P2 is going to be equal to 9.2 times 6.92, 4.18. Actually, sorry, 131.1 kPa. Okay, next one, 10-liter container, so that's volume. Pressure of 5.1 atm. Again, we're looking for pressure changes to 0.853 atms. We're looking for volume 2. Again, temperature is not mentioned, so we don't have to worry about it. Okay, so V2, our next new volume, is going to be 59.8. Oops, and this liters. 59.8. Okay. Next one, water vapor, we have 949 torr. Temperature this time, 298 Kelvin. And we're looking for the new pressure. So since it's a fraction, we're going to cross multiply. So P2 times 298 Kelvin is equal to 949 torr times 342 Kelvin. Divide both sides by 298 Kelvin. Kelvin will cancel. We're just going to be left with torr, which is what we want. So 949 times 342 divided by 298. That's 1089.1. Again, it's going to be torr. Okay, whatever unit that we're given is the unit that is going to come out in. Okay, remember that we want to make sure that the Kelvin temperatures in Kelvin and volumes in liters, so that we don't get mixed up for the ideal gas law. Okay, hydrogen gas, 6.21 kPa, and temperature of 413 Kelvin. Pressure is increased to 11.25 kPa. We're looking for the new temperature. Again, we're going to cross multiply. 6.21 kPa times T2 is equal to 11.25 kPa times by 413. Okay, I'm going to divide both sides by 6.21 kPa. T2 is equal to 748.1 Kelvin. Okay. Notice this next one has moles. That means that we have to use the other equation, the ideal gas law. Notice that the ideal gas law has N, and so N stands for moles. So we're going to be using that. So we're looking for moles. Pressure is, let me write out the equation. We call it PIV inert. So let's see, PIV inert, we have 5.6 atm as a pressure. Volume is 12 liters. We're looking for moles. Now the R value is according to whatever pressure unit we have. For ATM, we're going to look at our chart here. For ATM, notice it's this one because it has ATM in it. Okay, so 0.0821. 0.0821. And that's a constant as long as we're using ATMs. And sorry, we're not looking for moles, we're looking for temperature. We have 4 moles. Looking for temperature, so we're going to divide by 4 and divide by 0.0821. So temperature is going to be 5.6 times 12 divided by 4, and then be careful, you gotta divide again, or put everything in parentheses, otherwise your calculator is gonna get mixed up. So the temperature is 204.6, and this is in Kelvin. Okay. Okay, an unknown quantity of gas. We got 1.2 atm. Again, we're looking for moles, so we're using Pivnert. Volume is 31. We're looking for N. Again, we're using ATM, so atmosphere, so I'm going to use the same constant. Temperature is 87, but I want it in Kelvin, so I'm going to add 273 to that. So I'm going to divide both sides, isolate N by itself. Okay, let's see what N comes out to be. 1.2 times 31 divided by 0.0821 divided by 87 plus 273. Okay, 1.26 moles. Okay, temperature. So relationships, remember that, and we can derive all of our equations from this one from the combined gas law. Remember, if the variables are next to each other, they're inversely related. So pressure and volume are inversely related, which means that if pressure goes up, volume goes down. Okay, pressure goes up, volume goes down. Like for example, in your lungs, when you take a deep breath, the volume increases, and so pressure goes down. It's the opposite of this. So just like vice versa. Okay, when volume increases in your lungs, the pressure goes down, and that's why air can go into your lungs. However, if we have two variables that are above each other, like volume and temperature are directly related, which means if volume goes up, temperature also goes up. Okay, and vice versa. And so pressure and temperature are also directly related. Okay. So at high altitude, okay, what happened to the volume of a gas? So at high altitude, pressure decreases. So if pressure decreases, volume is going to increase, and temperature is going to decrease of a gas. Okay. Okay, moving on to semester 2 stuff. Covered acids and bases and solutions in Unit 9. So two parts of the solution, we have the solute and the solvent. Solvent is what you have more of. It's what does the dissolving. So if I had a beaker of water, the water is a solvent, and then if I had a little can here with salt, okay, the salt would be the solute. Okay. Characteristics of a solution: the particles are atomic size, so it is transparent. You can see right through it because the particles are so small. Okay, and it is homogeneous, which means that it's all one layer of stuff. You don't have things floating around in it, as opposed to heterogeneous. Okay, which means that they're, like for example, dirt and water, or sand and water, there's two layers, or oil and water, there's two layers, and so there's two things that don't mix together, and so it'd be heterogeneous. Okay, and then we also will be giving you this solubility table on your final exam, which you can use. It'll be stapled to the back of your final exam for your reference, and so you have to know how to use this. Remember that, like say I had sodium sulfate and I asked you what if it would be soluble or insoluble in water. Okay, so how to use this chart is you would look for either sulfate or sodium. In this case, sulfate is right here, and if it's with these guys, these cations, remember that the cations are always first, anions are always second. is with these cations, it would be insoluble, which means that it would precipitate. PPT would precipitate, it wouldn't dissolve. However, in this case, since it's sodium, it's not one of those 6 cations, it's any other cation, so it would be soluble, which means it would be aqueous. Okay, it would dissolve in solution. Okay, so make sure you know how to use this table. Oh, here's some examples. So NaCl, so Na, pretty much anything with Na is soluble, so I'm going to put AQ. Okay, AlPO4, so again I'm looking for aluminum or PO4. PO4 is over here, and notice it's any other aluminum is not listed there, so it's insoluble, so it's going to be solid. Okay, NO3, anything with NO3 is soluble. Al2S, so Al is not in that top row, so it's any other cation would be solid, insoluble. AgCl, Cl's here, Ag's here, so it's insoluble. CuBr, which by the way I'm writing S not for soluble but solid. Okay, so aqueous means that it's soluble, dissolves in water. Solid means that it's insoluble, doesn't dissolve, it forms a precipitate. Okay, Br, CuBr, insoluble. Okay, I'm gonna erase this. Let me use a highlighter. So RbNO3, Rb, where is Rb? Okay, Rb is up here. Okay, any cation soluble. Okay, calcium carbonate, so again, carbonate's right here, and it's any other cations are insoluble. HgI, mercury, Hg is going to be insoluble. And then ASO4, arsenate, is right here. Let's see, arsenate is here, and it's with Al, which is any other cation, so insoluble. Okay, so that's how you do those, guys. Okay, moving on along, we talked about solubility chart, how to use this. This is, again, for 100 grams of water. So if it's not in 100 grams of water, you have to multiply it or divide it to get to 100. So looking for this question number 4, at 20 degrees Celsius, what is the most soluble? Most means we can dissolve the most solute in it, so it'd be this guy, NaClO3, sodium chlorate. And then the least soluble at 20 degrees would be this one right here, so that's KNO3. Okay, soluble means that we can dissolve it. Okay, next, if I have an unheated solution, that's a keyword. It's made out of 103 grams of NaClO in 100 grams of water, 40 degrees. This is really important. Temperature is always important, so we're using 40 degrees. Saturated, supersaturated, unsaturated. So it's 130 grams, which is right here. Okay, 130 grams, 40 degrees, and it's 100 grams of water, so we don't have to divide it. Notice that it is on this line, and so at this point it would be saturated. Okay, if it was above that line, we would have to heat it up in order to dissolve it, and if it's below that line, that means we can dissolve even more, so it would be unsaturated. Okay, next one, would I be able to dissolve 100 grams of NaClO in now notice 200 grams of water, so we're going to divide this to get it into 100 grams, so divide it by 2, so 250 grams, and 80 degrees, so 80 degrees, 250 would be way up here, so like somewhere over here. Okay, would I be able to dissolve it in 80 grams of water? And the answer is no. Okay, because it's above this line here, it's above the NaClO line, and so in order to dissolve more, I have to heat it. Okay, to make it super saturated. Okay, now kind of the reverse question, how much NaCl could I dissolve at 80 degrees in 400 grams of water? So at 80 degrees, if I have, let's see, 80 degrees at 400 grams of water, okay, I'm looking at how much I could dissolve. So NaCl is over here. I'm looking for where it intersects this line, which is right here, which is 40. Okay, so I can dissolve 40 grams in 100 grams of water. So if I up that to 400, okay, I just multiply it by 4. So that'd be 160 grams. Okay, it can dissolve 160 grams. Okay, if you want to do the ratio thing, you can do that. That sometimes helps me. Okay, so make sure the water's on the bottom, 100 and 400, and then grams are on top. And we're solving for x, you just cross multiply, solve for x. Okay, same thing here, KNO3, 80 degrees. Okay, look for where it intersects that line, so right here, which is 170. So I can dissolve 170 grams in 100 grams of water. So if I have 400 grams of water, I'm going to have to multiply that by 4. So that'd be 170 times 4. So that'd be 680. 680 grams. Okay, pH, pOH. We have that on the back of your periodic table. So put it over here for our reference. Notice that pH, all of that stuff is right over here. Okay, so if I have 0.01 molar of HCl, HCl is an acid. Remember, if it has an H, it's probably an acid. If it has an OH, then it's probably a base. So pH is equal to negative log of that, negative log of 0.001. That's going to give me the pH since it's an acid. So negative log of 0.001, 2 zeros. Okay, it would be 3. So pH is 3. Okay, this guy, if I take the negative log, now notice this would be of OH, so this would be the negative log of OH is going to give me the POH. I take the negative log, which is fine. So let's do that. Negative log of 3e negative 5. So actually this is pH, POH is 14 minus 3, so 11. Okay, so the negative log of that would be the POH. POH is 4.5, so that means the pH of this NaOH would be 9.5. Okay. HCl is an acid, so if I take the negative log, it's going to give me the pH. Negative log 1.3 e to the negative 11. So that's 10.9. So pH. POH is 14 minus that, so what is that? 2.1. 3.1. Okay. Last one, OH is a base. So if I take the negative log, it's going to give me the POH. So POH is 0.25. pH is going to be 13.75. Okay, so that's how you do pH and pOH. Okay, pH 0 to about 6 is acidic, and then basic is 8 to 14. 7 is neutral. Okay, so it's neutral. Bronsted, Lowry, Arrhenius stated that if it has an H, it's an acid. If it has an OH, it's a base, or if it produces that in solution. Bronsted, Lowry said that if something is a proton donor, it's an acid. And if it's a proton acceptor, it's a base. Okay. If I combine HCl and NaOH, what would that give me? So it would, outsides and insides, almost like a double displacement, NaCl plus H2O. Okay, it's always going to make H2O and a salt if you combine an acid and a base. Say the same thing here. Outsides, insides, so we get sodium sulfate and water. Okay, moving on along. Okay, making solutions. We're going to use this other equation. Let's see, where is it? It's over here on your, okay, right here. Oops. I'm going to use that equation. MV equals MV. Okay, MV equals MV, that's the equation we're going to use. So M1 V1 is equal to M2 V2. So M is molarity and V is volume. So if I have a solution of 3 molarity, what volume would I need to make to get 100? And it has to be in liters, so it's going to divide by 1,000. Move it to the left 3 times to get 0.1 liters of a 1 molar solution. Okay, so solve for V. V1. Okay, it's going to be 0.1 divided by 3. So 0.03 liters. Okay, same thing for this guy. Okay, the next problem, again using the same equation. We have 1.5 molar. Again, looking for what volume I'll need to add to it to get 0.1 molar. And 500 milliliters, again, divide by 1,000 to get it into liters. Okay, so solve for V, divide by 1.5, so let's see, 0.1 times by 0.5 over 1.5. Okay, 0.03. Okay, or 30 milliliters. Okay, solution of 2 molar. Oops. What volume? 0.01 molar. 500 mils of it. .01. Okay, V1 is equal to 2.5 times 10 to the negative third liters. Okay, next one, molarity. So molarity, remember, is moles over liter. So if I have 5.5 moles over 3.4 liters, that's going to give me my molarity. Okay, 1.62 molar. Okay, molarity is a concentration, how concentrated the solution is. Okay, next one I have 3.2 molar. How many moles do I have? So I'm solving for moles. I have 3 liters. So I'm going to cross multiply. So X is going to be equal to my molarity. 3.2 times 3. So 9.6 moles of it. Moles of NaCl. Okay, and then remember that from this equation, how do I get moles? Moles, and by the way, this equation for the molarity is on the back of your periodic table. So let's see, right over here we have it. Your molarity equation is right over here. Okay, so moles over liters. But from that, remember that to get moles, we take whatever grams divided by the molar mass to get moles. So what we could say then, if we substitute it, grams over molar mass over liters. So if I want grams, I could plug everything back into this. The only thing I need is molar mass. However, since it's the same problem, 9.6 moles of it, I can also solve it this way. Okay, the molar mass of NaCl, if I look at my periodic table, let's see here, periodic table. Sodium is 23, chlorine is 35.5. So 23 plus 35.5 would give me 58.5. Okay, so 9.6 times 58.5 divided by 1 is equal to 561.6 grams of NaCl. Okay, moving on to Unit 10. This is thermodynamics. We're looking at exothermic and endothermic. If you look at this reaction, we can see that delta H is negative, which means it's exo. Another way to tell is if there's the words heat in the products, then it's exothermic. Or if we have those graphs, right, if we end up lower than we started with, we lost energy, it's exothermic. Vice versa is true if heat is in the reactants, or if this number is positive, or if it ends up higher than normal, or higher than we started with, then it's endothermic. Okay, but this one is exothermic. So exothermic, and how many kilojoules per mole will be released if I have 21 grams of carbon monoxide. So this is for 1 mole of carbon monoxide, so I have to first get that into moles by looking at the molar mass. So if we look at carbon and oxygen, so 12 plus 16 is 28. Okay. And actually, sorry, mix this up. It's 28 grams per 1 mole, dividing by 28. And then, if I notice that this is kilojoules per mole, so I'm going to multiply whatever I get by negative 113 kilojoules per mole to get kilojoules. So let's see, 21 divided by 28 is 0.75. So 0.75 of a mole times it by 113, I get negative 84.8 kilojoules. Okay. Okay, same type of problem, except this time we have 3 grams of SiO2. So again, I have to get that into moles. So if I look at SiO2, okay, again I have oxygen, silicon is 28. So 28 plus 16 times 2, which is 32. So what is that? 28 plus 32 is 60. Okay, and again, you're going to multiply by this. Notice this is endothermic because it's a positive amount. I gain in energy. Multiply that by 624.6 kilojoules per mole. Okay, so let's see. I have 3 divided by 60.05 moles, 624.6. That'd be 31.2 kilojoules. Okay, 3 laws of thermodynamics. First law is energy, what we call the conservation of energy. The energy can neither be created nor destroyed. It's always transferred. 2 is the entropy law. The entropy of the universe is always increasing. Okay, disorder. Another way to think of entropy is disorder. The universe is constantly spreading out and becoming more and more disordered as time progresses. And then the last one is what would it look like if there's 0 entropy? So entropy approaches 0 perfect crystal at 0 degrees Celsius, or 0 Kelvin, sorry, 0 Kelvin, okay, which is the coldest temperature we can attain in our universe, 0 Kelvin. Okay, heat corresponds to how much heat an object can absorb before changing temperature. That's what we call specific heat, or C. Okay, and so, for example, and this would be given to you, these values are constant. 4.18 joules per gram degree Celsius is water. Water has a very high specific heat capacity compared to like lead. I think lead is 0.92 grams per joules per gram degree Celsius. Okay, so if we compare those two, so this is lead, Pb. Okay, water absorbs this much amount of heat before it changes 1 degree Celsius. Lead absorbs this amount of heat, or joules, before it changes 1 degree Celsius. So if we think about that, if, let's say, I applied 5 joules of energy to both of them, same amount, let's say I had 1 gram of each, okay, notice that every time I hit 0.92, that lead is going to change 1 degree, and so this lead is probably going to change about 5 degrees. Water, however, is not even going to change 1 degree. It's going to it's going to change. It's going to absorb 5 joules of energy and change about 1 degree, little over 1 degree. Okay, so water can absorb 4.818 joules before it changes temperature. So the higher that number, the less it changes temperature, and the lower that number, the more change in temperature happens. And that's also why Hawaii doesn't have very drastic seasons. It's because we're surrounded by water. The temperature doesn't really change very much year-round. Okay, what are the 3 modes of heat transfer? So we have conduction, convection, radiation, and what is the difference? So conduction is when we have heat transfer through physical touch or contact. Convection is through the air or fluids, so it could also be like boiling water, convection. And radiation is through space, is through electromagnetic radiation, so like your microwave, UV rays, okay, which can transfer through space. It doesn't need molecules. Other two need molecules. So conduction would be like your frying pan, okay, on a stove. On a stove, there's a heat transfer there. Okay, direct physical contact. Convection, let's say you had a beaker of water and you had a boiling egg. Okay, that egg is receiving the heat from the water. Okay, that would be convection. And of course, radiation is microwave. Okay. Okay, which of the following, exothermic or endothermic? How do you know? Okay, would it feel hot or cold? So again, because this one ends up lower than you started with, it lost energy, it's exo. This one ended up with more energy, so it's endothermic. Exothermic reactions release energy. It releases energy, so it'd feel hot to the touch. Endothermic, they receive energy, they absorb energy, so it would feel cool. It would be absorbing energy from your hand. Delta H would be negative for endothermic reactions, and delta H would be positive for endothermic. Okay, exothermic negative, endothermic positive. Okay, now notice we can calculate for the amount of energy or heat energy in a given chemical reaction using this equation, and again point it out on your equation sheet. So let's see, where is it? Right here, QE equals MCAT. Okay, and we also give you some specific heats for water that are always used. So Q equals MCAT. So we have 5 grams, that's the mass, heated from 20 to 80. Remember, delta T is always final minus initial. Okay, whenever you have delta anything, it's going to be final minus initial. So the final temperature was 80 minus 20. And the specific heat of copper, which would be given to you, 0.092. Okay, and we're going to solve for Q. So 5 times 0.092 times by 80 minus 20. Okay, it'd be 27.6. Okay, 27.6 joules. Okay, 20 gram granite boulder. Let's see, granite is 0.1 calories per gram. That's important, the calories. 29 minus 10. Okay, so because of that, our answer is going to be, and actually I messed up on the last one too. So since it's in calories, I'm going to end up with calories, not joules. So I have 20 times 0.1 times 29 minus 10, and that would be 38 calories. And these are small calories. The calories on your food labels are kilocalories, so 1,000 of these. Okay, how much heat is released when 30 grams? Again, 30 grams. 1 calorie. And it goes from, notice final is 25 minus 96, so this is going to be a negative number, which means heat was released times 1 times by 25 minus 96. Okay, so we get to negative 213 calories. Okay, so it released that much amount. Absorbed would be positive numbers. Okay, 3.1 gram ring is using 10 calories, so that goes in for Q. We're solving for C. Rises 17.9 degrees Celsius. Okay, so solve for C. I'm going to do 10 divided by 3.1 divided by 17.9. 10 divided by 3.1 divided by 17.9. Or you can put it in parentheses. You could put the whole bottom part in parentheses in your calculator. So C is going to be equal to 0.18 calorie divided by gram degrees Celsius. Okay, moving on along. Temperature of sample water increases from, we have 5650 calories of heat. We're looking for mass this time. Specific heat is 4.18 joules per gram degrees Celsius. Okay, and let's see, we have 46.6 minus 20 degrees Celsius. Okay, and actually, for this problem, notice since we have calories and joules, I cannot actually use this value. I need to use the specific heat of water in calories, which is in this problem, 1 calorie per gram degree Celsius. I'm going to change that out. 1 calorie per gram degree Celsius. Okay, again, solve for mass. So I'm going to do 46 minus 20. 46.6 minus 20. Okay, that times 1, which is the same thing, divided, and then I'm going to do 5650 divided by that number. Okay, don't get that mixed up because I'm solving for m. Got to get m by itself. So 212 calories. Oh, yeah, actually 212 grams, since we're solving for mass. Okay, temperature of a sample with iron has a mass of 10 grams. It releases 47 joules. Mass is 10 grams. Okay, I'm looking for specific heat of iron. It goes from 50.4 to 25. Again, final minus initial. Solving for C, so 47 divided by 10 divided by 25 minus 50.4. Again, you can put the last part, the bottom, all in parentheses, 10 grams and 25 minus 50.4. Okay, so I get 0.185. 0.185 joules per gram degree Celsius. Okay, notice that it releases, so this actually should be negative, so that's why when I got a negative number in my calculator, I didn't account for that negative. Specific heat should always be a positive number. Okay, specific heat should always be a positive number. Okay, next one. I have okay, we're just for practice sake, I'm gonna turn this into joules. So I have 54 joules, and that's equal to the mass times specific heat is 0.092, and we're looking for final temperature, TF minus 25. Okay, so what I'm going to do is I'm going to distribute this to the TF and then solve for it eventually. So I'll do it over here, actually. 54 joules is equal to 4.5 times 0.092 times TF minus 25. Okay, what you could actually do is divide, well, here's what I would do. So I'm going to do 4.5 times 0.092. Okay, so I get that number. So 4.14 times 10 to the negative 1 TF. I'm going to distribute it. Minus, times that by 25. So is that 10.4. Okay, 54 joules. Okay, I'm going to add 10.4 to the other side. So 54 plus 10.4 gives me 64.4. Okay, and then isolate TF, divide that 64.4, whoops, by 4.14 e negative 1. Can I get 155.5 degrees Celsius? Okay, so final temperature. Okay, a couple more. Okay, we have 569 joules of energy. Notice it's absorbed, so it's positive. 155 gram mass. Looking for the specific heat, and it's heated from 40 minus 25. So let's see. 569 divided by 155 divided by 40 minus 25. Okay, so specific heat is going to be equal to 0.24. And it should always be a pretty small number. It should always be in the decimals, unless it's like water. Okay, specific heat of an unknown substance. It releases 12 joules, so negative 12. Mass is 2.5 grams. Looking for specific heat, and it goes from 25 to 20. Okay, final minus initial. So again, solving for C, I'm going to do negative 12 divided by 2.5 divided by 20 minus 25 to get C by itself. C is going to equal to 0.96 joules per gram degree Celsius. Okay, so that's how you use Q equals MCAT. Name energy transformation. So nuclear, remember that there are 6 main energy transformations. There is nuclear, there's thermal, okay, there's radiant, there's mechanical, chemical. Okay, so nuclear bomb explodes, that's nuclear. Okay, it releases heat, which is thermal. It also releases radiation, so that would be radiant. And then it would also release debris, which is mechanical. Okay. And I forgot electrical. Okay, electricity passes, so that's electrical energy through a light bulb, causing the tungsten filament in the light bulb to heat up, so that would be thermal. And when the metal is hot enough, photons of light are emitted, so that would be radiant. Okay, car engine, electrical spark, again, that's electrical. Ignites the fuel-air mixture in the piston, thermal. Okay, it ignites, there's fire. Explosion and heat cause a cylinder to expand, so something is moving, that'd be mechanical. Okay, and actually I missed one, so be careful. Whenever you have fire, that's actually going to be chemical. Okay, so chemical is whenever there's a fire or an ignition. Okay. In the sun, we have nuclear fusion, so obviously that's nuclear. Compresses hydrogen atoms into helium, releasing heat, so that's thermal. Okay, the heat energizes electrons, so that's electrical. And that produces light, so radiant. Okay, so anything that has to do with electrons is electrical. Anything that has to do with heat is thermal. Fire, or whenever you have atoms that are doing stuff, that would be chemical. Okay, solar panels, voltaic cells, positive and negative fills of silicon, photons of light, that would be radiant from the sun. Okay, hits the silicon and knock off electrons, so electrical. Okay, 3 different types of energy transfer. We already mentioned that: conduction, convection, and radiation. What are the main ways we can speed up? So this is now unit 11, which kind of bled into unit 10 a little bit. So there's 5 main ways. Okay, we can increase the concentration. We can decrease the volume of the container that it's in to make the atoms closer together. We can increase the temperature. We can add a catalyst. Okay, and the last one that we can do is we can increase the surface area or make it into smaller particles. Remember that the smaller the particles, if we have dust as opposed to a single granule or a single piece, it's going to react faster. Okay, this is unit 12, equilibrium. Okay, this is Le Chatelier's principle. Le Chatelier's principle. So, looking at this chemical reaction, remember it's kind of like a balance, right? And if I were to remove A, okay, it would kind of shift it this way, right? If I took off weight from the left side of this reaction, the balance would kind of angle this way. So in order to restore balance, it's going to shift to the left to bring it back into equilibrium. If I add more C, same thing, I make the right side heavier, and so to balance it out, it's going to shift to the left. Okay, so it's going to shift to the left. Not the KEQ, same thing as KEC, doesn't change unless there's temperature. So I can just kind of negate those. Adding more C is going to shift it that way too. Increasing temperature, I got to look for the word heat, and same thing. If I have my balance, okay, if I add heat, it's going to shift this way, or it's going to unbalance it this way, so it's going to shift to the right to bring it back into balance. And when it does that, remember that it's shifting to the products over reactants. So you put a KEQ. So when I'm making more products, it's going to make that overall number bigger. Overall KEQ is going to get bigger. For pressure, we just have to look for the side with less moles. Remember, it's opposite. Moles, less moles. So these are the moles. This side has 2, this side has 3, so it's going to go to the side with less moles. If I decrease pressure, it's going to go to the side with more moles. Adding a catalyst doesn't actually affect the shift, but it does affect the speed of the reaction. Okay, so that's Le Chatelier's principle. Another thing for Le Chatelier's principle is how to write out the equilibrium expression. So just to review that real quick. Remember, products over reactants, so it's going to be C, and since it has a 2 coefficient that goes as an exponent, over A times B. Okay, and that's going to equal to KEQ. Okay, and we could also use, there's things like icebox and xbox that we could use to calculate for those values. Okay, redox. Redox is unit 15. Okay, unit 15. So looking at NO, we talked about oxidation numbers. We can gather those from the periodic table, from just looking at the charges. Okay, the different charges, which are at the top of the periodic table. Transition metals don't have a charge, so we have to look at what's connected to them to determine their oxidation number. And then we always go with oxygen and hydrogen first, along with halogens. Technically, the rule is whatever has the highest electronegativity takes the oxidation number. So basically, the negative cation usually takes precedence. So look at NO. We're going to do oxygen first since it has an oxygen. Each oxygen is -2. And there's 2 of them, so a total of -4 charge. The overall charge is 0. There's no, charge next to it like this sulfate ion in our next example. And so it has to equal to 0, so nitrogen has to be 4. And there's only 1 of them, so it takes on that full +4 charge. And that's how we can determine oxidation numbers. Remember that oxidation numbers is for just one of the atoms. Okay, so for example, the oxidation number for oxygen is -2, not -4. -4 is the total. Okay, same thing here. Oxygen is -2, total -6. The overall charge has to be 0, so sulfur has to be +6, but this time there's 2 of them, so that +6 has to be divided by each of those 2 sulfurs. So each sulfur is +3. Again, I just circled the oxidation numbers. Okay, polyatomic, so sulfate. Again, water is -2. There's 4 of them, so -8. Now this one is tricky, a little tricky, because it has to equal to -2, not 0. So we got to kind of think in our head, how do we get -2 from -8? Well, if I add 6, it's going to turn out to be -2. So sulfur, there's only 1 sulfur, so sulfur has to be +6. Oops, and I messed up. This should be total charge of -8. Okay, moving on, determine the oxidation numbers for these guys. So again, oxygen is -2, total -8. It has to equal -1 charge, so Mn has to be +7. This one, -8, has to be equal to 0, so +8, and there's 2 of them, so +4 for nitrogen. Chromium and chromate, so again, -2, and doing the oxygens first. This has to be equal to -2, so chromium has to be +6. And I don't know why the blank's there, but it should be +6. Okay, that should be over there. Okay, this one, again, I'm going to do oxygens and hydrogens first. So oxygen is -6. Hydrogen is +1, so how do I balance this out to 0? Nitrogen has to be +5. Okay, I know it doesn't say that on your periodic table, right? Nitrogen is supposed to be -3, but remember that if there's an oxygen or hydrogen, those guys take precedence, and then whatever is the negative anion takes precedence. Okay, this one, -2, -6 has to equal to -2, so +4. And then Cl and ClO, again, oxygen is -2. Chlorine has to balance out to -1, so chlorine has to be +1. Again, you can see how the oxygen took precedence there. Oxygens and hydrogens take precedence. The rest has to kind of balance it out to 0. Okay, so -2, -10, since there's 5 of them, P has to be +10. And then, so each is +5. This one, -8, has to equal to -2, so +6. Divided by 2, +3. And last one, notice, single element by itself. A lot of people forget this rule. But if you have a free element by itself, it's going to be 0. Okay, redox. So we're going to have to do a bunch of things. Going to have to assign oxidation numbers. That's going to allow us to tell what's being oxidized, reduced, what the different agents are, and then the direction and total electrons transferred. So for this one, hydrogen, oxygen, they're zeros because they're free elements. Water is -2, +1, total charge of +2. Okay, so from this, and I'm going to just do this already, since there's a 2 here, that 2 has to multiply. So it's going to be 4 hydrogens, so +4, and 2 oxygens, so -4. Okay, so if I look at this, hydrogen goes from 0 to +4, and oxygen goes from 0 to -2. So because of that, hydrogen, it gets more positive. Remember, the acronym is Leo the lion says grr. Loss of electrons is oxidize. Gain of electrons is reduce. Or you can use oil rig. Okay, oxidation is loss. Reduction is gain. Okay, remember one of those two. So hydrogen, since it lost electrons, it became, remember, electrons are negatively charged. And so if you lose electrons, you become more positively charged. So hydrogen lost electrons, got more positive. So because it lost electrons, it is being oxidized. Okay, and oxygen gains, and I'm just going to put it down here, 4 electrons. Since it got to -0 to -4, it's being reduced. And then to assign agents, it's just the opposite of whatever it is. So since hydrogen is oxidized, this is going to be the reducing agent. Oxygen is going to be the oxidizing agent. And we can say that 4 electrons went from hydrogen to the oxygen. Okay, next one, I'm going to, free elements right away are 0. Sodium is +1, chlorine is -1, and there's ×2 since that coefficient applies to both of them. Okay, so again, I take a look, sodium and chlorine. So sodium went from +2 to 0. So gain 2 electrons. So it's reduced, and oxidizing agent. Chlorine went from -2 to 0, got more positive, so it lost 2 electrons. It's oxidized, and it's a reducing agent. Okay, so the electrons went from chlorine to sodium, 2 electrons. Okay, last one, combustion. Here's a free element. Let's see, C2H4, so hydrogen is +1, so total +4. Carbon has to balance that out, so -4, and there's 2 of them, so -2. Okay, this oxygen is -4, +4, and then -2, +1, +2. Oh, and then the coefficients. So this multiplies to that +2. So +4, -4. And this 2 multiplies there, so +8, -8. Okay, and this one's a little tricky because there's double oxygens there that we got to combine. So let's see. So carbon, and notice here that hydrogen's oxidation number doesn't change, so hydrogen is not a key player. Carbon goes from -4 to +8, so it lost 12 electrons. The difference is 12 electrons. Okay, lost 12 electrons, so since it lost electrons, it would be oxidized and the reducing agent. Oxygen gained 12 electrons, So let's reduce and the oxidizing agent. Just to double check, so oxygen went from 0 to -4 plus -8 is -12. Okay, so matches up. So we can say then that 12 electrons went from the carbon to the oxygen. Okay, last unit, unit 16, organic chemistry. We're going to name the following compounds. Remember that single bond, if it has all single bonds, it's an alkane. If it has a double bond, it's an alkene. And then if it has a triple bond, it's an alkyne. And then the prefixes, if it has one carbon, it's a methyl group, 2 is eth, 3 is prop, 4 is bute. Me eat peanut butter, me eat peanut butter. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Okay, so this one has 3 carbons and a double bond. So 3 is prop, and then propene to double bond. Okay, the next one is eth to 2 carbons, ethane. Next one is 2 carbons again, so eth, but a triple bond, so ethyne. Next one is 4 carbons, so it'd be bute. And there's a double bond, so butene. Okay, next one is 1, 2, 3, 4, 5, 6, so hex. And then 3 carbons is ine. Next one is 5 carbons, so pent. And it's a double bond, so pentene. Next one, 2 carbons, eth. And then double bond is ethene. Next one, 1, 2, 3, 4, 5, 6 carbons, so hex. And then triple bond is hexine. 1, 2, 3, 4, 5, 6, another 6 carbons, so hex. Double bond is ene, hexene. Okay, a couple more. 1, 2, 3, 4, 5, 6, 7, 8 carbons is oct. No double bonds or triple bonds, so octane, like your fuel. 1, 2, 3, 4, 5, 6, 7, 8, another 8's oct, but there's a double bond, so octene. And last, a couple more. Ethane, so single bond, so ethane. This one is bute, triple bond, butyne. 1, 2, 3, 4, 5, 6. Hex, triple bond is hexine. 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be dec. And there's a triple bond, so decyne. Okay, molecular formula. So remember that for alkanes, it's CnH2n plus 2. Enes is just CnH2n, and then ine is CnH2n minus 2. So this one, ane, so F is 2, so C2, H2n plus 2, so double that plus 2, so 4 plus 2 is 6. Okay, propane is C3, again, I'm going to double that, add 2, so 6 plus 2 is 8. Okay, propene, I just double the amount of carbons. Okay, enes are the easiest ones, you just double it. Okay, propyne, you double it, minus 2, so 6 minus 2 is 4. Okay, octyne, again, C8, you're going to double it, minus 2, so 16 minus 2 is 14. Nonene is 9, so just double it, since it's ene. Hexene, double it. Butene, double it. And heptyne is going to double minus 2, so double 14 minus 2 is 12. Okay, functional groups. Okay, again, you're just gonna have to, it's not gonna be as hard as this review. It's gonna be multiple choice, so you just have to select the best option for the final exam. But I'm just gonna go over these real briefly, so you have an answer key. This is an alcohol with a crown, so it's a carboxylic acid. Okay, this one is an ether with a crown, so it's an ester. Oops. And you know, it might seem very difficult for you to identify these things, but when you take OChem, since you work with it so much, you naturally memorize it. So one day, maybe you guys will memorize it. This one has an N, with a double bond, so this would be an amide. Okay, an amide is an amine with a crown. Okay, this one is an alcohol. Notice there's no crowns next to it. This one is a halide because it's a halogen. Okay, Br, iodine, chlorine, and fluorine, they're all halides. Okay, or halocarbon. Okay, functional groups. So this one is an aldehyde. Okay, a crown with a hydrogen. Okay, carboxylic acid. This one is alkene. Okay, this one, carboxylic acid. Okay, this one, our first ketone. Notice that there's a carbon on both sides of the crown. Kind of looks like a key too. Alcohol. Alkene. Oh, sorry, alkyne. Okay, this one's alkene. And you can, by now, you should be able to identify it as propene. This one is 1, 2, 3, 4, 5, 6 hexyne. Okay, here's another ketone. Okay, there's 2 carbons there. Okay, this one is aldehyde. Okay, because of that hydrogen. Okay, alkyne. 1, 2, 3, 4, 5. It's pentyne. This one is another aldehyde. A lot of aldehydes in here. Okay, this is alkane. No double or triple bonds. And then alcohol. Okay. And that's the end of our final exam. Congratulations for making it this far. Good luck on your final exams. Godspeed on your final exams. And keep up the good work.